JC is a PhD candidate in computer engineering at real-time embedded software group at the University of Waterloo, and has over 10 years of experience in data analytics, pattern recognition, statistical modeling, and machine learning. So JC has extensive works, including writing software for safety critical systems for leaders in the transportation industry, including QNX and Bombardier. So now, welcome our GC, our speaker.
Yeah, just before I start, I want to get a sense of background of people in the room. What kind of stuff have you guys been studying? Or is it mainly engineering, science, like data science? Do we want to give me an example of
all three above?
Pardon?
All three above.
All three.
Yeah, I think different people represent different groups.
All right, perfect. Okay, I think this is going to be interesting then. So, thank you for the wonderful introduction. My name is Jean-Christophe. You can call me JC or JK, as it may be. I'm the CTO and a co-founder of Acerta. And I'm going to talk a little bit about Acerta, but I mainly want to talk about what makes quality data, or what makes data quality. And I'm going to try to keep it a little bit general, but I am going to go into specifics about more automotive applications, and in particular, applications in manufacturing. So basically, over the past few years, cars have transformed, and they're transforming at an incredible rate. This is a picture of a wire harness from a modern car. Actually, not even that modern. This was about, I think, 7 years ago already. And as you can see, there's a lot of wires connecting a whole bunch of stuff. So basically, what's in here is between 50 and 300 ECUs, or embedded computing units. These things are little computers that control or measure data from the car, or controls its operation. It'll control things like the combustion and how that works, or the transmission and how it changes, or your electrical power system, all kinds of stuff about the car. And with this complexity, this increasing complexity, the car becomes more and more difficult to diagnose in terms of its problem. So if something goes wrong, it becomes much more difficult to figure out what exactly did go wrong. And while you're building it, it's difficult to tell whether or not you actually did it right, because it becomes so complicated. But a benefit of this complexity and this computerization or electrification is that cars now generate an enormous quantity of data. So how much data? It turns out that during the process of manufacturing, yearly, factories generate about 809 petabytes of data while building cars, which is a pretty incredible number, I think. And incredible, especially when compared against the amount of data that's generated by cars on the road, which is only 93 petabytes, almost a tenth. That's kind of crazy. Like, when you think about how much data is actually generated while making a car versus what's generated by that car while it's running, it's kind of nuts. But this represents an opportunity. This data is extremely valuable for optimizing manufacturing processes, or understanding when faults occur, predicting when faults occur in the manufacturing line, optimizing the plant KPIs, or detecting or predicting faults before they occur, while the car's even driving, potentially. Sorry?
Quick question, is this per car or total?
This is definitely not per car, absolutely not. No, this is the entire automotive industry, period. So like, every single company that manufactures even an automotive component. So everything from the earliest part of the supply chain all the way up to when an OEM releases that car. That's what's being generated in the 809 petabytes. Versus 93 petabytes, this is the data generated by all the connected cars on the road today. Does that make sense? Yeah.
Google vehicles? Like autonomous vehicles?
I don't know if that's included in this number. I'd have to check the citation. But obviously they're going to generate a huge amount of data. Any other questions? Yeah?
Does it differ greatly between different car manufacturers?
Oh, 100%. So there's a couple different manufacturers, like Nissan, for instance, they don't generate that much data. But if we look at General Motors car, they're going to generate a huge amount. And what's really interesting is, well, I'm going to talk a little bit more about what makes quality data versus not quality and what that is like, but it isn't just about the amount of data you collect, but also how you collect it that makes the difference.
Just a bit on what does it mean actually 93 petabytes? Does it mean interaction with infrastructure on the road? Because we don't have really at the moment still, even in our big cities, good infrastructure that goes, in an intelligent way, communication between car and what is going on the road.
So not all of this 93 petabytes will even be collected by a centralized data management system. In fact, a lot of this data is going to be generated and then maybe aggregated before it's sent out. So all these little ECUs in this car, they're going to generate a lot of information, store it in a buffer, usually a circular buffer, and if anything goes wrong, they'll collapse it and summarize it and then ship it out. That's the typical connected car kind of process.
So any node in that previous picture is a circuit, that's a
This is
computer?
It's a modern wire harness. There's many computers in a modern car, between 50 and 300 in some cases. And they're running millions of lines of code. It's kind of crazy how complicated cars are becoming.
Because I see some dots there. Those could be sensors.
Yeah,
or-
they could be sensors, they could be other types of equipment. Yeah, that wire harness is really the nervous system, right? It connects everything, not just the computers together. They're running. Really, cars are now just kind of rolling computers more than anything else. They just happen to have engines because they need to move. So this data represents an opportunity for industry to transform. So industry's gone through multiple different transformations over its existence for the past 100+ years. So the first innovation was really like power, and then it was electrification, so like using electrical power to get things done. This obviously improved how people were able to accomplish tasks in the manufacturing line, but also it was the production lines, and then the computerization of the production lines, what are called like manufacturing execution systems, MES systems. These things control everything that goes on the line. It makes it more reproducible, more reliable, more controlled. Industry 4.0 is really the transformation towards IoT, where those MES systems that are controlling all of this manufacturing, they also generate and collect a lot of data about what's going on so that you can understand better when something goes wrong, or potentially learn how to optimize the process. So Industry 4.0 is really where Acerta is kind of centralized. That's what we're attempting to help companies achieve. Right now, the industry is basically in Industry 3.0, and it's shifting towards this vision of a connected plant. So Acerta sees itself as the analytics supplier for automotive. We want to be the analytics supplier for this data. We want to be involved in the process of vehicle manufacturing right from its design all the way to its inception, and finally to when it's decommissioned. We kind of want to be the analysis tool from cradle to grave of the car, in my opinion. Our reach is global, so we have customers including GM, Nissan. The three down here you might not recognize if you're not in the automotive industry, but Dana, Aisin, and Musashi are all tier 1 manufacturers. They build components that go into cars. So people choose us because we specialize in automotive applications. We concentrate solely on automotive. We don't touch any other industry. That's very intentional. We believe it's extremely important to speak the language of the industry that we're working with, not just because we want to be able to extract domain knowledge from our data and understand it very well to improve our models' efficiency, but also because once we generate results, we need to be able to communicate those to engineers and line workers so that they understand what the results of our model is telling. So we have a team with an extensive AI and automotive background as a consequence. We also have this perspective of data that should be holistic, right? We want to collect the entire history of the car in our database. And we're on-premise computing enabled. This doesn't matter as much for you guys, but essentially it lets us deploy models as executables directly to the line, so that model doesn't rely on the internet, which is very important for manufacturing applications where if the internet goes down, you don't want your line to go down. So that's all I'm going to talk about for Acerta. I want the rest to be about data science, but I feel like as a C-level executive in my company, I got a pitch. That's just a fact. So I'm going to talk mostly about quality and change and how that affects data science with respect to manufacturing and industry. Yes?
Do you use any of your models to go into setting warranty policies and pricing and everything sort of from a financial standpoint?
So the way that our models touch warranty is that they'll actually attempt to explain the warranty case from the manufacturing data. So if we find a correlation between manufacturing data and a warranty case, that'll inform us of how to improve that product. But if we can't find that correlation, it might be further evidence, for instance, that actually the manufacturing process was carried out successfully, and it may be a point of use, like the way that the product was used that caused the recall.
Right.
And that's very useful information for a corporation.
Sure.
But they may not act on it. They're probably going to still treat it as a warranty.
Right.
Does that make sense?
Yeah. Thank you.
Yeah, no problem. So there's basically 5 aspects of quality that I want to talk about. The top 3 you're probably familiar with, you get a background in science, so accuracy, precision, and repeatability. These are basically qualities that tell you, or qualities that you might be interested in for evaluating how good an experiment design is. But there's 2 extra here, traceability and completeness, that I'm going to talk about as well. These are outside of the concept of a scientific experiment, and they're necessary for making good data sets from real life, because unfortunately real life is not an experiment. You don't have this experiment design giving you that traceability and completeness that you would otherwise have. So let's talk about the first 3, accuracy, precision, and repeatability. So these plots represent those concepts, which is generally, it's fake data, don't worry about it. We'll talk about accuracy first. So represented in this plot is measurements from 2 devices, a calibrated and an uncalibrated device. So a calibrated one is going to tell you, it's going to give you an accurate measurement. What that means is that the measurement corresponds to reality. If I measure a pencil that's 5 centimeters long, it's quite a short pencil, fine, and it turned out that my ruler is telling me it's 10 centimeters, and my ruler is not accurate. It's not telling me the truth. So the problem with calibration affects manufacturing a great deal, and that's because the measurement devices that are used in manufacturing are used 24/7, 365 days a year. These things wear out, they become miscalibrated, and that's a very significant problem for both the processes that test systems that are generated from the manufacturing process, but also for diagnosis. So these plots up here, it's about 10 plots of 10 different signals measured during the process of manufacturing an axle assembly, which is actually pretty complicated. If you've ever had a chance to look at them, they're a large collection of gears, and sometimes in the case of hybrid cars like that, they become very complicated because they incorporate a motor and other things. These measures are used to determine the quality of the differential as it makes its way through the line. And what you can see in different colors is the distribution of the data collected from these devices as they're manufactured over time. And you can see that for each color, there's quite a significant difference between months. For what would otherwise be a largely computer-controlled manufacturing process, it's surprising to see such differences month over month. And this could be either from calibration or there are kinds of problems. If we zoom into case measure 2, and across 2 months, we can see that there's a pretty significant difference in both the mean and standard deviation across these 2 months, 2 adjacent months. This could be from lack of calibration, maybe the device became miscalibrated, but it could be from the suppliers. What if we're getting steel that's low quality? It could be from process adjustments, so maybe I've changed the process slightly to address another quality issue. It could be from employee schedules, so humans are still involved in the process, they still have an effect on it. They can still change the outcome. And finally, the weather. Things like the weather can actually affect the quality of the part that's manufactured, because temperature and barometric pressure can affect some manufacturing processes. But if we don't know that our devices are calibrated and that we're getting accurate measurements of reality, we can't differentiate any of these problems from our manufacturing process. And that goes for our models too. If our models are looking at this data, we won't be able to tell the difference between a process that's changed and a device that's become miscalibrated. So this affects even sensors that affect acceptance criteria. So this is the same set of differentials. Clearance A, clearance AB, and clearance B are all measures that are used to determine the performance of a particular differential. It basically represents the distance between gears, which greatly affects its operational efficiency. Even here, you see significant differences. This should be a clarion call to check your calibration and possibly update your models, retrain them, you might think. we actually take an approach where for models that are deployed, if we notice a change in the data that we observe month over month that we believe is a systematic one, for example, the steel supplier change, we might actually choose to train a new model for that month, or maybe a new model every month to try and explain that line. Whereas if it's a seasonal change, something that happens repetitively or periodically, we might choose to train a single model and wrap up all of that together. It really depends on the nature of that change. We've realized over time that it's important to consider these possibilities in examining this kind of drift over time. And as a consequence, we've started to build a framework internally for normalizing the differences between our models so that we can run batteries of models against each other and figure out what strategy or what model archetype is best adjusting to the drift that we observe. So Coliseum is basically our MLOps system. It allows us to scale the exploration of architectures and paradigms across a large compute cluster that we have internally. It lets us tune hyperparameters, track the data that the models were trained with. It lets us version the dependencies as well, so we can track the dependencies of the models via Docker and similar. And we can actually export the model architecture as JSON so that when we want to reproduce a result, we can grab that architecture and that data and reproduce it. So it also lets us deploy those models because it can package them for deployment using Kubeflow. To give you a sense of what the data science life cycle is at Acerta and how we operate, we collect data from our customers and perform data ingestion to normalize all of the data that we collect. We have an internal system for tracking manufacturing data. We'll talk a little bit more about that later. We query that and we put it into Jupyter. We start processing it using our cluster, and we build a set of models. Each model and all the data, all the artifacts we generate gets tracked. Right now, we're actually using MLflow for tracking these artifacts. When we're ready to deploy a model, we end up using Kubeflow and Kubernetes. So when we set up this process, we were designing it around adapting to drift. So as we notice drift, we start to build a system for tackling drift automatically. We have a system that automatically retrains models that have been deployed to Kubernetes. So when we detect drift from the data that we ingest, using our monitoring system, we generate events that indicate the type of drift that we observe so that we can respond to it most effectively. That might mean training a new model each month, as I said, or updating an old model with new data. And here you can see kind of a little bit of the workflow. Basically, the trainer tests a bunch of models or different model pre-training strategies, registers all the results, and if we find a model that's better than what's already deployed, that model will go through acceptance testing as part of CI/CD. Are you all familiar with what CI/CD is or DevOps? It's like a release management system, it's an automatic process, essentially, of doing acceptance testing on a software product. It's the same thing for machine learning. This is kind of a newer concept in the world of data science. I think Microsoft coined the term MLOps this year, in fact, but it's becoming increasingly important to operationalize machine learning in a very automatic and very repeatable way, because it's become too manual to generate all these models and deploy them over and over again, especially as we realize that we need to adapt our models over time. So the lessons from accuracy, essentially, are that we need to monitor the data as it is ingested. We need to check for problems every time we notice drift, and classify them into calibration issues or otherwise, and we need to respond to them dynamically. So we need to be able to adapt our models constantly in order to deliver quality results. So we're going to talk a little bit about precision. This one's much shorter, mostly because solutions to this can't really be system. If when measuring something, you're using a device that is imprecise, you're going to find that your results are poor. So let's say, again, to go back to the example of the differential from before, you have on the y-axis clearances A, B, and B, and on the x-axis a couple of different values. What you'll notice is that for values that are not used for acceptance criteria, we have a great deal of resolution. In other words, you see these black bands because all those values are kind of packed. But for the values that are used for acceptance criteria, they're very discrete. You don't have values measured in between those values, or in between those bands. That's because the device that they're using to measure, or the caliper that they're using to measure this distance is actually not that precise. They're trying to measure millimeters with meters. It's not going to work. You would think that you'd be able to foresee this problem and design your process around it, but the truth is you have to make sure that your process is adaptable as a manufacturer. Just because you think you've got it figured out at the beginning doesn't mean that you'll realize that a problem later that you need to account for and adjust for. So, in conclusion, just I don't really have better advice to solve that problem because you just need good tools. That's it. For repeatability, this is a problem or that comes up in experiment design where if you do the same process with the same input, you get the same result. And you would hope that that's the case, but in manufacturing, that's not always the case. In fact, you can see 3 examples here that are kind of problematic. This is actually the same EPS system, or electrical power steering system. So when electrical power steering systems are tested, you check whether or not vibrations from the ground reach the steering, because that makes for an uncomfortable ride. You don't want to feel the road with your hands. So they usually check for vibrations in this data. The problem is, well, you could punch the mic, as it turns out. And this test is unreliable because there's so many things that can leak into your vibration sensor that you wouldn't expect. So they need to repeat this test many times, 8 times in fact, to get a reliable result. So in these 3 instances, somebody's kicked the microphone or something, and you've ended up with bad data. So if you have a problem like this, you need to approach it systematically. You need to run the test multiple times if you can't make it reliable, or adjust the process until it is reliable. Or you need to adapt a system where, as with our monitor previously, if we detect drift, we send it to our sanity checking service, which basically collects data from that set and determines whether or not the data collected makes any sense whatsoever. You might think that that's kind of a silly thing to do, but it turns out that we see data that makes absolutely no sense whatsoever quite frequently when a sensor goes bad, for instance. We've seen case measures that have reported distances that are the size of the entire factory, which is obviously wrong. That shouldn't happen. This is the kind of sanity that I'm talking about. I'm not saying does it meet any small criteria or acceptance bands or whatever. I'm saying really big differences between our expectations and reality. When you do come across such things, especially in a systematic way, you want to report those either to your user or to yourself so you can adjust. So the lessons for repeatability are really about reporting unreliable measurements or adapting your processes if possible and monitoring your data for sensible values. This is something that we need to do whenever you ingest new data set. So that's it for the scientific properties that make quality data. I'm going to get into more detail about the things that you have to account for when you're not dealing with the formal scientific experiment design. And if you excuse me, I'm just going to sip. Yeah, I ran out of moisture. Sorry about that. So, traceability. What is it? Traceability is about identity. And what I mean is, when data is traceable, you can identify the exact source of that information, the exact source of that data, which is a really important concept and a very difficult one to get a hold of in the manufacturing industry. So what I have represented up here is a manufacturing line, a very simple one, incorporating only 3 operations and an end-of-line test, that's DOL. So each of these processes are generating incoming data. And to create a complete picture of what I'm building, let's say I'm building a transmission. You all know what a transmission is? So let's say I'm building a transmission. Let's call the transmission John. Calling it a name to emphasize the fact that identity is important in this case. When I'm building John through his first run through the manufacturing process, when does John become John? When does the transmission become a transmission? From the perspective of a manufacturer, it's when it's complete. But what if I'm trying to model it? I want to know data from operation number 1. What if it doesn't even have a serial number? I still need to be able to identify it. I still need to connect it to John, because if I want to build a data set out of the data collected from all these operations, I need to join it together. That means I need an identity to assign for that data. So John really gains this identity in operation 1. So this is kind of like one of those philosophical problems where I pile sand and such and determine when the grains of sand become a pile. The truth is, even 1 grain of sand is a pile. And from the perspective of data science, I need to know exactly where a chunk of data came from. So what if it fails? What if John fails us? And it turns out we need to fix John. Well, typically what happens is we'll go back to an earlier stage of the process, take it apart, replace the part, test it again, see what happens. So we'll run John through the ropes again. This is kind of a ship of Theseus problem, right? I'm pulling planks off my ship and I'm replacing it with fresh timber. Is it the same ship? Anybody want to hazard a guess? No? The answer is it's a different ship. In fact, any change that's made to the transmission makes it a new transmission. This is no longer John. This is like Dave or something. So now that we've got Dave, I guess it's sensible that it's generating a new set of data and Dave has different data. That's fine. Maybe it's very similar data, but that's fine. It's a manufacturing process. It should all be pretty similar. What if it fails again, but we don't need to go all the way back? What if we're only generating data from operation number 2? And now we make Tom or something, I don't know. We have now 3 transmissions, 3 independent separate transmissions, but the third one has a unique problem. It doesn't have any data for operation 1. What do we do? Who wants to guess?
You take the data from the second run,
Yeah,
and add it to the third.
for sure. That's a completely valid approach. And in fact, that might work. But if you do that, you gotta be really careful. So if you do that, and you take Tom, and you put Tom in your testing set, and you put Dave, number 2, put Dave in your training set, you're now leaking information about your training set into your testing set. Because operation 1, that data, it makes it into your testing set. So if you do that, which is completely valid, you need to be extremely careful about how you separate your data into different places. So in conclusion, each assembly has a different identity, even if it has the same serial number. So serial number is not correlated to your identity. But also, you need to be very careful about how you isolate data once you assemble it for your training set. So let's talk about completeness. What does completeness mean? Does that involve? So completeness is really about measuring the right stuff. So that sounds like a simple enough task, but the problem is not about necessarily measuring the right stuff, but being able to adjust what you're measuring over time in a manufacturing setting. Because you may find that your manufacturing process has problems that you didn't anticipate. That means measuring new things. If your system is set up in such a way that it's difficult to measure anything, that's a problem. So like, we're looking at an engine and we're trying to characterize the quality of the combustion in that engine. We're going to look at the inputs to the combustion and the outputs. The inputs in terms of air, fuel, oxygen, pressure, temperature, those kinds of things. And we're going to look at the output, like NOx, or remaining oxygen, CO2, CO, those kinds of like chemical outputs. If we're missing some of these values, it may be difficult to characterize their combustion. That means maybe we'll need to add sensors in the future if previously we were just worried about engine temperature and overheating. So measuring or dealing with completeness isn't just about measuring the right stuff, but also getting the right amount of stuff. So let's say we're measuring not quite sufficient data to reconstruct a signal. This is a very simple one. A red signal represents a sine wave. Treat it as reality. This is the signal that we're trying to represent in our data. And we've taken a sample of 3 points, which generates this nice blue curve, which looks absolutely nothing like reality. We're trying to model a process that evolves over time. We can't simply assume that our samples are good enough. Who's familiar with Perry Micros? Nobody? Oh, all right. Well, Harry Nyquist is going to haunt your dreams if you deal with time series. Even just increasing the amount of data you collect blindly is not going to be enough. You actually need to understand some of the properties of your data. That means, what is the Nyquist rate? The rate at which you can reliably reproduce the original signal in the rigor sample, I mean, to be specific. So let's say we sample with the Nyquist rate. Well, it turns out you get a very nice sine wave reconstruction. Maybe it doesn't look perfect, but it's not bad. We got a problem though. So this is automotive, or at least my problems are in automotive. Automotive uses something called CAN bus to transmit data across that wire harness that I showed you at the beginning of the presentation. CAN bus has a number of problems, chief among them being the amount of data sent in each packet. Basically, every time I want to send a message over CAN bus, I have 8 bytes that I can put that into, which if you don't know anything about bytes, that's basically nothing. So I have to make a sacrifice when I send a message. When I send a message, I have to choose. What signal do I send? How often do I send it? Typically, what happens for signals that may not be mission critical for the car or for the part, I'm going to send signals, let's say, aperiodically, or somewhat at random. If I do that and I try and use the Nyquist rate to guide how much data I can render, I'm going to get pretty garbage results. As you can see, this looks absolutely nothing like sine wave. So what do? I have to really understand my data and the way that I'm collecting it in order to collect good data. And to do that, I have to know, in this specific example, what my interarrival time is. As you can see, the interarrival time, which is the time in between samples, on average produces a mean which is far from my Nyquist rate, which is bad. I want the mean of my interarrival time to mirror the Nyquist rate of the signal. If it does, then I get an Nyquist construction. So this is the kind of level of detail that you need to dive into when you're measuring data about a system. You really need to worry about not just what you're collecting, but how you're collecting it, how much of it you're collecting. What's the rate? What's the sensor like? There's huge amounts of limitations that you need to consider when dealing with real production scenarios. We can't all have nice sensors. We can't have tons of expensive sensors. It's not always a science experiment. Sometimes we need to build systems that are cheap.
A question. So here the time is in seconds. You have it on the bottom?
Yes.
So, because I'm familiar a little bit with Azure machine learning analytics stack.
Okay.
So they can put like, I mean, when we are talking about how often you measure, you can put it like, like have almost like real-time streaming data coming to your machine learning.
Yeah.
So what will be the issue having something like that? It will be too much data, or you are worrying that...
Too much data, yeah. So the problem with cars is that as a consequence of the bus that's used for communication, you're limited in what you can transmit in terms of the volume.
Oh, okay.
So you have to make sacrifices. That's why this kind of stuff happens. You have to sacrifice something. Something's got to give. So what if we make different kinds of stuff? Most manufacturing lines don't make one product with one model. They might make several. And the funny thing is, a lot of these different product models are made by sometimes completely different people who have very different ideas about how stuff should be named, which is very frustrating. As you can see here, we have many different names for basically the same data. And what you need to do whenever you're processing it is have really good metadata. Just because the machine reports these values to me, I'm not satisfied with that. I need to know, what is the name of the signal, what unit is it, what was the measurement device. I need to know all this kind of information to actually process it and compare things across different product models. And sort of the way that we deal with a lot of these problems that I've discussed about completeness is Cortex, the system that we have internally for ingesting data and normalizing it, putting it into a normal form, or for reporting when data doesn't meet the quality standards set by the negotiation between us and our client. From that normalized data structure, we can actually extract data in the shape that we want for various different applications, AI or otherwise. And the system has been designed around manufacturing data and automotive data collected during driving situations. So this system is really good at capturing that kind of information. So kind of the lessons to learn about completeness are really around planning to adapt the data that you collect over time, and knowing how to collect data for your specific use case, knowing exactly what the nature of that data is and the collection mechanism, and also planning to adapt to changes in that data over time. You can't assume that the same people are making your product all the time. Yeah.
Why should well, you kind of described it very nicely, the process itself and measurements have to be adaptable
Sure.
to the dynamics. But who told us that the functions that we're considering have the Fourier transform to apply the Nyquist theorem? I mean, Nyquist theorem is the connection between continuum and discrete processes.
Sure.
And definitely you may have much more frequencies not to necessarily be able to apply the Nyquist theorem.
Yes. So when you set out to design a system for collection, you need to understand the requirements. So maybe you can't capture all the frequencies that you need to, right?
Exactly.
But that might be a sacrifice you have to make as well. You may need to choose what level of aliasing you're willing to accept. And if you have to accept that, then you have to accept it. There's no alternative. Is that kind of?
Yeah, exactly.
It's really a matter of.
But, you know, kind of my only point that definitely, I mean, in this area, sometimes it's kind of dangerous even to apply the Nyquist theorem, although it's the only strictly mathematical tool that we have.
Yeah. So
That's true, but
the way that you deal with that too is, so if you're designing a process around such a theorem, we also have to account for lots of variability in the equipment that you're using
Sure.
and all that stuff. So
Absolutely.
just take it and double it. Like if you're an engineer, you design the theorem, you do all this stuff, and then what you multiply it by 2 or 10 or 30,
sure.
and then the problem is solved. Like, is it robust enough to not crash? Okay, great. Double it.
So they're kind of like a human intelligence here rather than artificial.
Yes, so that's kind of the perspective that I wanted to give quality from industry, like doing this stuff for applications where like dollars and cents matter. Just to give you guys a different perspective. So this is actually everything that I wanted to talk about today so far. So if you have any questions or you want to learn more things or whatever, just go ahead and ask. Yeah.
Do you see a big difference between classical cars and electrical ones?
In terms of
Manufacturing, I mean.
sure, yeah. The complexity of the power delivery system is completely reduced, right? It's a fraction of what a combustion engine is going to do. The combustion engine, like the modern combustion engine, I say modern probably with large quotes, because I mean, it hasn't fundamentally changed that much in the past 100 years or whatever. It's extremely complicated. And an electrical motor or an electrical power system is very, very simplistic by comparison. And as a consequence, likely much more reliable.
How about the battery? You know, can you rely on the battery?
The battery correspondingly is very unreliable. And that's probably the big problem with electric cars that we're working on.
Correct me if I'm wrong, but I think you're passing a very important message here that effectively if we have data
Yeah.
which is already unreliable,
Yeah.
we could make very big mistakes. And
Absolutely.
therefore it is extremely important, you know, to preserve this reliability and, as you call it, adaptability
Yeah.
during the process of collecting this data.
100%.
And this is indeed, not many people kind of passing through this message. Usually the approach, in many cases in data science, hey, we have this big chunk of data, let's kind of extract useful information out of that. But that information could be far on.
Yeah, in fact, you could easily lie to yourself. I mean, there's a saying about data, right? Torture it enough, Yeah.
And they do say, the IBM summer is big data is 4 weeks. One of them is the velocity, so the uncertainty, big noise is in there.
Yeah.
So I have a quick question about, so
Sure.
you get data from manufacturing directly,
Yeah.
and how much time you spend on running the data to kind of clean up, make sure it's okay to go ahead and to do the modeling?
I think the very first time we approach a data set in a new company, it's always a very long-winded exercise. Mostly because data collection practices across companies are very different. Some people have a very advanced system where they track and monitor almost everything. And other companies might just keep a couple of Excel files on a Windows server or something. So the process varies wildly. After that initial kind of adaptation phase, the amount of time spent wrangling data goes down significantly. But still, I would say the amount of time that we spend on feature engineering is probably larger than the amount of time we spend making these models. Especially in manufacturing applications. In automotive applications, it's a bit different because we're dealing with much more complex, like on-road applications are much more complicated because you have to deal with time series. That means that the architectures that you have to use here in neural networks get much more varied and complex. But for manufacturing, the models are usually simpler because you're really after not prediction but inference. You want to understand why your model is making a particular decision instead of making it produce the best prediction. If that makes sense.
So when you look at unique models for different manufacturers, do you create your own optimizers and loss functions, or do you use like some stable ones in some cases?
So most of the time we've used things just like Adam, and that's been enough for the optimizer. For the loss function, though, we can get pretty varied, and sometimes we actually incorporate dollar cost in our loss function because that will get you the best result. Not in terms of its accuracy, but in terms of its actual monetary output, right? So you don't necessarily want to optimize a model for producing a good prediction. Sometimes you want to optimize it for producing the most money. I'd say those cases are still pretty small, only 10% of the models that we generate. That makes sense.
And we continue on this question, like what is inside of this optimizer? What mathematical tools are inside of this, block that you have?
Talking about Adam or
Optimizer, basically. When you are saying, okay, what sort of loss function to choose and things like that.
Yeah.
So effectively you are solving some optimization of the whole problem. What is inside there? Do you have like choices in which cases what to choose? How to optimize?
You can put almost anything into a cost function that you want. Whether or not that's going to generate a useful result is a whole other matter. And typically you want certain properties out of your loss function, like you want it to be, you want it to be curved. You don't want any like local minima. So there's some like general advice about making the cost functions that applies for the most part, like make it quadratic or something. Make it explosive increase of cost or loss as the error increases, right? You want the solution space to be bowl-shaped. Does that make sense? Because if you think about it, your model is kind of like a ball rolling in a bowl. You want the loss function to look like a bowl as a consequence. Does that make sense? Yeah.
Are you able to share some of the models, or, for example, a specific manufacturer step? You use only one model, or sometimes you have to adapt to a different one depending on.
So that's an interesting question. So if I look at a manufacturing process as a sequence of operations, most of the time the manufacturer has each individual operation pretty well figured out. I'm not going to say 100% figured out, but they're going to have a pretty good idea of what they expect as the output of that operation to be. What manufacturers don't do a good job of right now is collecting and collating that data across all of the operations and extracting insight from that picture. Does It's a much more complicated thing to do, and they don't really do it as a matter of course. So it's kind of a new thing for them. Does that answer your question?
If you address the first one,
Okay.
if you have some examples of, if you can share that, of machine learning models
Like-
that you apply.
Okay, so like architectures kind of?
Yeah, the type of machine models.
So some of that is IP, so I'm not going to dive too deep into that. But it being time series, you can probably wager a few educated guesses about what types of layers we put in our model architecture, like LSTM and WaveNet and similar. But I'm not going to dive too deep into the architecture. I'm sorry.
That's fine.
Yeah.
How much of an impact do the models actually make on the manufacturing process?
Sure, yeah. So manufacturing is usually evaluated in a couple different KPIs, key performance indicators. So how good a plant is doing is based off of a few different things, like first time quality. So like, does freshly manufactured transmission pass the end of line testing process for the first time? So the rate at which that is accomplished is a really huge KPI. Typically, manufacturers will run about 95%, but each of those percents is like $1 million per line, in some cases per month, in other cases per year. So increasing that FTQ by a tiny bit is a huge deal. There's also rework rates. So when something doesn't pass the first time, it has to go through and be reworked. That's the difference between like John, Dave, and Tom, right? That process is very expensive, and so the rate at which units have to be reworked is also usually incorporated. This is sometimes represented as a cost or a ratio or otherwise. And then the last one is, what else? There's another one. I'll think of it, but basically our impact has been on the order of up to 5% in FTQ for some of our manufacturers or some of our manufacturing customers, which is quite a big deal. Does that kind of answer your question? Or?
Yeah.
Yeah.
Just a curiosity.
Sure.
You mentioned that Nissan, for some reason, does not collect a lot of data during manufacturing process. Is it a good thing? It means that they do that so precisely. In fact, incidentally, I was on assembly plant in Kitakyushu, in Japan, Nissan example.
Yeah.
And it was 15 years ago.
Mm-hmm.
And I haven't seen any human there. 15 years ago.
Yeah.
So it was absolutely automated, and I was absolutely impressed. I cannot compare like with other, competing car manufacturing companies, but so I'm just curious your comment. Like, does it mean that they do that so well they don't need to do like anything in addition?
So just a point of clarity for that one. When I was saying they collect less data, I was referring to on the road. So Nissan cars, as they're driving,
Okay.
collect a fraction of the data.
Not during manufacturing.
During manufacturing, they're actually quite comparable. In fact, I'd say Nissan might even have limits out there.
Mhm.
But I don't want to make too many comments about the customer.
So how many employees in your company, and how many data scientists?
Circuit is now at about 32 data scientists, 8 data scientists right now.
So for example, if you hire 3 of us, Sandy, Freddie, and Peter,
Sure.
and we have different levels of data skills.
Yeah.
So do I actually have the chance to go through the data wrangling, data modeling, and do the final products?
Yeah, in fact, we might contribute to our library of tools. We maintain a large set of libraries that we use for pre-processing data, building models in an automated way, and it's all kind of integrated into our Coliseum system. Basically, we have a standard protocol for communication between model components and build up pipelines. It's very similar, actually, in concept to Kubeflow. In our integration with Kubeflow, we translate the model pipelines into a Kubeflow pipeline in that way. So you might implement one of those steps, or you might implement a brand new model, but you'll probably end up touching data and building at some point during the internship.
No, because my level is so low, I always have to handle data cleaning.
Sure.
So I don't want to just focus on in-house. So how many interns do you have per year?
We usually have for data science group between 1 and 2 interns. I think right now we have 1 intern. Yeah, we have 1 intern.
So if our data science students are interested in working in a company, can they contact you or?
Yeah, for sure. My email's right here.
Okay. Yeah. So I like that, yeah. Okay.
Okay.
Any other questions?
I was wondering, thinking that, for example, Elon Musk's Starship now has troubles to get finalized, and they also had issues with the SpaceX, booster landing and things like that. Can this system be used to optimize the manufacture of like unique product like rockets and stuff?
Probably, yeah. I mean, a lot of the models that we build have a lot of automotive domain knowledge built into them, but the core principles remain the same between different mechanical systems. The problem for us as a company, however, is that it isn't just about data science. We also have a sales team, business development, and a network of connections that make us successful in the automotive industry, right? It's like a whole picture that we need to assemble to sell to enterprise and a sector like that. So if we were to do that, we'd need to probably change the entire organization in order to accommodate a customer like that, if that makes sense.
But technically it's feasible, yeah?
Technically feasible, sure. Yeah, I would say so. Yeah.
Can you use patents for your models, or is that possible?
So we've spoken at length multiple times to patent lawyers, and basically said, you know what? Okay, don't even bother. Keep it a government secret. And that's probably the best way to do it, because really it is an algorithm, and algorithms have a kind of complex history and interaction with patents, and that you pretty much can't patent them. So even if you manage to successfully patent it, defending the patent is really a matter of who's got the most cash. For a small company, it's just better to keep it a secret. Sure.
I was wondering how accurate are your machine learning models, because they are not 100% bulletproof, yeah?
Sure, yeah. In fact, a lot of the time, you don't even necessarily need accuracy. Accuracy might even be a bad measure, because when you're measuring how well a model is doing for a particular manufacturing line, consider that the majority of units that are generated by that line should work. It's the minority that don't. You might be inclined towards using things like AUC that are slightly less biased. I say slightly because even AUC is subject to bias of some sorts. So you need to be careful in defining the metrics that you use to evaluate how good a model generates. In our case, I would say it's on a case-by-case basis. I think it really depends on the application and what it's being used for. So as an example, for a manufacturing model that's attempting to build, this terminology used a lot, a digital twin, where you model the process that's being used in the line, better understand how different components of that process affect the whole. For models like that, you only need AUC of about 80 in order to gather useful insight. And our models are typically well above that, but even when they're below, it's still useful insight. It means the data you're collecting from your process is not informing you of how well it will do in the end. That's actually useful information all on its own.